Hello, good afternoon. I ask that all of our presenters turn on their cameras and their mics at this time. A warm welcome to everyone that's joining us. I'm going to get us set up. We'll get our presenters on and sharing the presentation, and we'll be off to the races. All right, everyone's on. Thanks, guys. So may the 4th be with you. Today, we're having this conversation around the intersection of hardware, software, and data, specifically focused on large-scale metal AM. We are open to Q&A and chat throughout. So if you look over on the right-hand side of your screen, there's a chat frame, and there also is a Q&A frame. If at any point you have a question during the presentation, you don't have to wait till the end. You are welcome to put those out there, and you can also, come in with some chat. So feel free to say hello, give us your favorite Star Wars character, whatever. We'll kind of try to pay attention, and we'll make this a bit more interactive. So as you explore your chat, I'd like to give you a quick overview. We're going to talk about some of the opportunities and the pain points of large-scale metal AM. And then we're going to talk about the software and the data aspects of simulation, inspection, what's unique about repair, and what these three gentlemen think about the future of large-scale metal AM. After that, we'll have Q&A, and then we'll go back to the tables for networking sessions. So I want to do a quick intro. Bhaskar is joining us from DM3D Technology. He is the president and COO. He has a PhD in metallurgy and 31 years of metal processing experience, 18 of those in AM. Patents and publications, and engaged with the industry. So lots of knowledge to tap into there. Jeff joins us from Hexagon Virtual Manufacturing and Costing. He is the director of global BD. He's going to be representing the simulation side of things for us today. He is a mechanical engineer. He was a Marine Corps officer. Thank you for your service. And also had a background with Fiat Chrysler. Our final panelist is Giles, who is the commercial business manager for structured light scanning at Hexagon Manufacturing Intelligence. It's a very long title, but his experience certainly warrants it. So he's going to be bringing about the metrology side of things. He is also a mechanical engineer, but he has 25 years of non-contact scanning experience. So if you have metrology questions, he's your guy. He also is very involved across the industry, SME, AMUG, Rapid, ASME. So I really just appreciate you guys joining us today. And to kick off, I'd like Bhaskar to give us a brief company overview and a little bit of a description around the DM3D powder-fed DED process.
Hello, everyone. This is Bhaskar from DM3D. So DM3D is a metal AM service provider, as well as we build and sell equipments using our proprietary process, direct metal deposition, or DMD, as we call it. This is nothing but a laser blown powder DED process with some closed loop controls and special features in the technology that we developed over the years. And using this process, our main focus is making mid to large size metal parts. And when I say large, I mean the largest part we have manufactured is about 10 foot tall, so fairly large size. And with different metals, including steels, Inconels, titanium, and so on. So we have a service bureau with multiple machines on our floor, a full machine shop, and quality control, and so on. So from product development to production, we do it all for our customers. And like I said, we also build and sell these equipments. And very happy to be here today to discuss the large-scale metal AM. Over to Laura.
Yeah, so Bhaskar, can you tell us a little bit of what we're seeing in this video and just like kind of break down at a high level those steps of the DED process?
Sure thing. So this is a typical simulation video first, showing like the laser shooting out from the nozzle and then metal powders getting injected into the melt pool that the laser is creating. And then you move the nozzle, put a bead of metal and step over, put second bead, third bead, and so on. And then that's how you create a layer. And then you stack up the layers, you create a full part. So you start like any other AM process. You start with a CAD solid model, CAD file, slice it between the different layers, and then tool path it, and then upload the data in the machine, and then process the part. Our machines are with full 5-axis capability, so you could do like significant amount of overhangs and complicated structures with this without support. But it's all, at the end of the day, comes down to simulations and software and process control and inspection processes.
Excellent. Thank you, Bhaskar. We're going to transition over to Jeff to give us a high level. Hexagon has a huge breadth. So I think it'd be great to give us a feel for that breadth, and then we'll kind of get into some of those specific topics today that you've been helping Bhaskar with as the process owner.
Yeah, thanks, Laura. So most people think of Hexagon, and if you're familiar with the name, they associate it primarily with metrology. But there's a whole lot more that we do as well. And so just one way of looking at it is that Hexagon touches 95% of all cars, 90% of all aircraft, 75% of smartphones, and 80% of orthopedic implants. So just to give a sense that they're kind of ubiquitous. Next slide. To take a look at the overall portfolio of Hexagon. So at the bottom is metrology. And this is, again, where people typically think of when they think of Hexagon, metrology hardware, software, and associated tools. But there's also the design and engineering, which is the section at the top. This is the company formerly known as MSC Software. So it's now been fully absorbed by Hexagon. So that is Nastran, Adams, Mark, Actran, Digimat, and a host of other tools across CAE spectrum. The box on the upper right, the manufacturing process simulation, is the one that I'm responsible for, metal forming, joining, welding, and additive manufacturing. And then in the middle, the production software, our tools, this is really everything that's related to the software associated with the production and manufacturing of goods. And so things like CAD, CAM, planning software, everything from CNC for metals, sheet metal fabrication, even woodworking, which was something I just learned about recently. Is pretty neat. So there's a host of very well-known, long-standing brands included in Hexagon. One that I would call out specifically is the Volume Graphics product. Is probably one of the most well-known, really incredible software, best known for its CT scanning analysis. I think they own about 80% of the market. But in addition to that, they also do great things with metrology within the VG platform. So that's a very high-level overview of Hexagon. Thank you.
Excellent. Thank you, Jeff. So whenever we were starting our conversations, we have a very complicated digital workflow that we'll look at on the next slide. But I appreciated Jeff's approach. He said it's really just 3 questions. What do I want? How do I get it? And then did I get it? So that kind of resounded with me. And the other thing that we always talk about is it all starts with requirements. So of course, it's the flow of requirements through your process and delivery to the final customer. So before I pull up the longer workflow, just remember, we're kind of sticking with those 3 main questions. The point of this is not for you to be able to read each of these process steps. It's more to reflect on the complexity of a DED-enabled product in the digital workflow. So within this, we've highlighted a few of the key software and data points. You will see one, which is where once we're actually thinking about how that additive part is going to be built prior to building it, simulation and in compensation, and a circle there. Then we have during the AM process, DM3D has a set of process control and data acquisition software that they're using for monitoring and control of the actual AM process. And then we have iterative steps throughout that manufacturing flow where we are likely understanding the shape, perhaps looking at the microstructure and additional things. So it's just important to note when we're talking about these large scale structures, often we're not talking about just one shape, but actually a series of shapes. So now that we've kind of thought about that, the other thing they'll kind of note, and we'll see within this, is you think about the large scale metal AM. You can't just take your giant rocket nozzle and say, go put it in a CMM. So conventional approach to inspection, probably not a possibility here. So Bhaskar, I'd like you to kind of walk us through some of these key steps, and particularly as the process owner, if you have some specific pain points when you're doing large scale metal AM.
Oh, there's so many. So yeah, large scale metal AM, it's great. I mean, it offers some unique benefits, particularly depending on parts, of course. For the right applications, it can save significant amount of cost and lead time. However, it's not free of its challenges. It's got its own challenges. One of the challenges, first of all, it's a new technology barrier, right? You're trying to replace traditional technology. It could be a combination of forging or casting or spin forming process. Some of these parts are made by forging, a lot of ring forgings and electron beam welding and so on. Some of these parts are made by spin forming. And you're trying to replace that with metal AM. First challenge is, the new technology. The challenges comes is like, how do I know that this process produces reliable material and material properties and quality? And there, the way to tackle will be like creating standards and material property data. I think those are extremely important things. So that when a customer comes, they already know that, okay, this material printed in this process will give this kind of properties, just like other processes. So creating that is a big thing, but providing that information to the customer is key, because they're often nervous about switching to a new process. The second is throughput and cost. I mean, yes, metal AM can cut down cost, but if we for select applications, but if we are to expand its portfolio and more and more applications, then overall cost has to come down. Now, the cost in a new part printing comes from two sides. One is the development cycle and then the production, right? The development cycle, typically metal AMs, go through several iterations before you get the part right. And that's where I think simulation comes in, and Jeff can talk about it better, that how could we use these tools to integrate with the process development and cut down the iterations needed during printing process. That will cut down time as well as cost. And then the second part of it is, of course, production cost. And how do I reduce the production cost? Large part means, longer time. And AM, as it is a slower process compared to many traditional processes. So to counter that, we built a new big machine for building big parts with multiple nozzles. It's fitted with 2 nozzles now, and it's capable of adding 2 more. So that will naturally reduce the cycle time to 1/4 with 4 nozzles. So the throughput and the cost are two key factors. And then comes, the last one is more like reliability. How do I know that I have a robust process? So it's critically important to collect the process data and analyze it and ensure that the input variables were good. And then in situ process monitoring and control is also equally important for large part printing. You don't want to print a part which is hundreds of thousands of dollars cost and finally say, oops, there was a problem, there was a defect or something not conforming. So I think these are some of the key points.
One quick question.
Yeah,
this came up in the Q&A. Someone asked, can you share a maximum deposition mass that you have printed in a component, just for a sense of scale?
So the maximum we have printed so far is 4,100 pounds, 4,100 pounds part, 10 foot tall and 8 foot diameter.
I think everyone can agree that we'll consider that large scale.
Yeah, it's a fairly large size, and Giles knows it well because he did all the inspection work there. And I'll leave it to him to talk about the inspection challenges on such large parts.
Absolutely. So I really appreciate, Bhaskar, how you related that back to like production and cost and all of those things that are required to, successfully manufacture and put things into production. So we've talked about the fact that there's a lot of heat and thermal going on when you're building with large scale metal AM. So I'd like to ask Jeff to talk us through a bit of the simulation loop that we're showing there as far as predicting, both from a shape standpoint as well as from a microstructure standpoint.
Thanks, Laura. So to follow up on what Bhaskar said, we're going to establish what the part we want, right? What do we want? And so in this case, you can see this animation of the test cone example that we used in coordination with DM3D. So you start typically with a CAD, and then there's some pre-processing, slicing, and path planning that takes place. And that's kind of what you think you should get. The other piece that needs to be defined is the near net shape, which is not CAD, right? It's something that's slightly larger than CAD. And depending on the process type that you're using, will define how much larger than the physical CAD net shape that you're going to require. So that's an additional step that needs to be defined as well, and it is important to note. And then beyond that, the next step would be to say, okay, well, how do I get it? And there's a couple of ways to look at it. The first would be just purely dimensional, and this is what we're looking at on the right-hand side to evaluate how that part is deforming as a result of the thermal strain during the build process and after cooling. The other aspect of it would be what's the microstructure that I'm going to get. So as Bhaskar mentioned, that you typically have to define the microstructure for the process, but the process can vary. And I'll just use his example of going from 1 print head to 2 to 4. Well, if you're going to go up from 1 to 4 heads, your cycle time is going to go down. Your thermal history is going to be drastically altered as well. The whole thing's going to stay hotter. It's not going to have time to cool down, and there's a lot more energy going in over time. So how is that going to affect the microstructure? Well, these are the types of things that can be evaluated as well through simulation, whether that's on this type of a part, which is axisymmetric. It's kind of just going round and round. It's a little bit more simple because it could be defined even as much down to a two-dimensional problem, two-dimensional axisymmetric problem if you really wanted to. But what about like a three-dimensional component that has different features and different orientations, and you have a more complex scanning strategy? So being able to evaluate for those, what's the scan strategy that I want to use? How much cooling time do I need? And what about for other materials? Like aluminum, for example, has a much higher tendency to misbehave if you get it too hot, and you'll just turn into a pile of peanut butter. And so, in an effort to avoid some of these potential pitfalls, it's a lot easier to try it via simulation than it is to try it via good old-fashioned trial and error, because the simulation gives you a lot more insight. You can see what's happening, you can visualize it, and you can probe it. Right? Think of it that you could put a probe anywhere within the part, even during the deposition. Now, tell me how you're going to put a thermocouple on the part, right at the deposit layer. Good luck, right? It's not possible. And so being able to take this data, draw some conclusions, and make some changes relatively quickly is really the value to bring simulation into the loop. One of the main things that folks often ask us about, or the kind of the number one thing, is say, but I need a compensated shape, right? I need to take that shape and invert it so that, if it's positive, I create the negative, and then it comes out nominal, right? And that is still the value, one of the big values of utilizing simulation. However, I would say that that's kind of the last thing, right? That's the last check, because really before that, you need to get to a stable process that's going to give you a decent microstructure with a high probability of succeeding, not having some other defects, right, of different types. And so these are all types of things that could be worked through. So I see that Victor has given us a great question. It's always the elephant in the room when it comes to simulation, is how long computational time it would be and number of elements. I don't recall the exact number of elements on this part, but we modeled this with a 2.4 millimeter layer height, which is approximately twice the physical layer height. And we're working on doing one that's at the actual layer height of 1.2 millimeters presently. So running this on a layer-wise basis where the entire layer is applied at one time, this simulation solved in about 48 hours for a thermomechanical, whereas the physical process took 96 hours. So it solved in half the speed of the physical process. Now, of course, if we go down closer to being a transient process of capturing the individual scan vectors, that could go up significantly. But the point about simulation is probably the number one challenge that we face, and it's still the biggest hurdle that we're working towards. We have made significant reductions. This has been our number one effort in the last 12 to 18 months, is to make the solve time go down dramatically. And I think Bhaskar can attest to how much better we've already gotten in that time since we've been working together. I think we've gotten on the order of 95 to 97% reduction. So something that would have taken 100 hours in the past might now take 3 to 5 hours. So we're certainly making some pretty significant improvements, and we're continuing to enhance that solve time. So, but to the point about solve time, just in the usefulness of it, going back to powder bed fusion, when simulation was coming on board there, everybody said, I need it to be faster than the physical process to be useful. And I would say that that still holds true, but it depends on the level of fidelity that you're going for. And really, ideally, it should be much faster, much like orders of magnitude faster than the physical process to really be useful. Because ideally, we would like to be able to run 10 different iterations in the time that it would take to build one, not just one iteration.
Yeah, we certainly see that. And I think it's something that's exciting because rapid computing, the capability is increasing all the time. But on the other hand, if you're within a manufacturing process, you don't necessarily want to need a supercomputer to do your computations for you. I really appreciate that, Jeff. We're going to transition now to the inspection side of the process. And then Giles provided a example here. So perhaps you can tell us a little bit of what we're seeing with the structured light and kind of the mechanics of that. And then we can kind of take it back out kind of to the broader. What are those main considerations during your manufacturing planning, specifically from the inspection and metrology side of things?
Right. Thank you, Laura. Can you hear me okay?
Yeah.
My name's Giles Gaskell. Yes, Hexagon's made its name primarily with metrology. And so we have the good fortune to have really the whole range of metrology devices available from all types of CMMs that you can imagine, portable CMMs, laser scanners, and this is a structured light scanner. And I just chose this example because the whole system fits on one screen, so you can see what's happening. And what you have there is a tool which would be very useful for small components, but also, as I'll show you in a moment, you can scale it up to big components. So the way that works is you have the sensor on your right, which is like a and there's another example. Yeah, just leave this one up for the moment. Can you run the video again? And then you can see how it works.
Figure out why it's not. Yeah. Okay, there it's going again.
Yeah, so if you want to take a picture of your family and get a good result, you keep this camera still and you keep the family still, and this is how this system works. But not dwelling on this particular system, I want to talk more about the application in additive manufacturing, because it may surprise you. It surprised me that people in additive manufacturing seem to have a reluctance to spend money on inspection, which is always seen as almost the last thing that you want to invest in. And that's strange because, in fact, the requirement for inspection is greater for additive manufacturing than conventional manufacturing. And the reason for that is, well, as you probably know, if you can't measure a part, you can't sell it. If you can't verify that it is what you think it is and prove that to your customer, then good luck selling it. And there are a lot of issues with additive manufacturing. that make the challenge all the greater. For example, you can have internal features and cavities that you can't even see. So if you can't see them, how do you measure them? It's a challenge. Another important thing to consider is that if you're conventionally machining a part from a block of steel, when you buy that steel, you'll have a certificate with it from its maker that says this is good steel and it's good all the way through. And that's the most you ever have to worry about. Whereas in additive manufacturing, obviously, you're making the material as you go along. And so how do you verify the quality of the material? So if you look at the next slide, this is just to show you, this is the biggest part that DM3D ever made, the 10-foot tall, 8-foot wide rocket nozzle. And so Bhaskar had exactly this challenge, that you have to be able to measure it to verify what it is you've made. And in addition to that, from Jeff's perspective, he can't calibrate his simulation. If you're simulating what final form you're going to end up with, you can't verify that you're doing a correct simulation if you can't measure reality and feed that back into your simulation. So you may be surprised. In fact, I was surprised. The technician that completed this work assures me that the measurement of this part was done to an accuracy of plus or minus 60 microns, which is really quite phenomenal. And I think, Bhaskar, it was useful to you, wasn't it, having this measurement data?
You're on mute, Bhaskar.
I'm sorry. Absolutely, Giles. It goes back to the same thing. What do I want and how do I get it, and did I get it, right? So without these measurements, we wouldn't have known where we are at the end, right? We did the simulation, we did the process and in between measurements, but at the end, it matters what we ended up with. And not only that, the second important aspect of the scanning measurements is when we take it to the next step for machining of the part, final machining step, it's absolutely important to know where the part is, what condition it is. If I have to adjust my datum because of the distortions to get a better fit or better machining. So to understand the machining strategy or to determine the final machining strategy, it is extremely important to do this measurements and then overlay the CAD and decide how to go about machining.
Yeah,
then
absolutely.
you need to do it again after finishing, the machining process.
Yeah, because it'd be so easy to scrap what could be a perfectly good part just for misunderstanding what exactly is you have. And so there's no answer to the question which people may be asking, what's the right measurement device for my process? And that all depends on, or mostly depends on the size of the part and the accuracy that you require, and whether you need data for absolutely everything, including the insides, which means you maybe have to go to CT scanning. But you wouldn't be able to do CT scanning on this part because there isn't a CT scanner large enough or powerful enough to actually measure this part all the way through. And so, if there was one, it would be extremely expensive. And you'd probably have to have a no-fly zone around it for the. You're laughing, but it's true. Ford Motor Company have a CT scanner that literally has a no-fly zone over it because of the amount of energy it emits. Yeah, so. Definitely plenty to keep metrology specialists busy. I see there's a question here. Could you comment if there's any measurement difficulty around the somewhat bright reflective surfaces that we get from deposited material? Yeah, that's a very good point, Victor. In some cases, yes. In this case, if you were to see this up front, I mean, it has got a certain amount of reflectivity to it, but you can't see your face in it. It's not that shiny. Generally speaking, if you can see your face in it, it's too reflective, and you would have to spray it with some kind of light developer spray. Nowadays, we have developer sprays that are temporary and sublimate. So you spray it on, it's dry, and in half an hour's time, it's gone, disappears, or an hour. But you get ones that last different lengths, and so that's a solution. But yeah, very good point. If it's really shiny, you will have an issue. Victor, thank you. Okay, I think that's it for me, Laura.
No, excellent. We appreciate that. I having come from the background that I did, where we were doing some large scale, but not necessarily this large of scale. It's interesting to see, and I think it's also interesting to see just there's inspection technologies and software that have advanced so much in the last decade, from when I started my DED and AM journey. So it's interesting to see how these things play together. And I think the other thing that we really harp on from the TVGA standpoint is, DFAM, MFAM, it's all designed for manufacturing. So as you said in our pre-conversations, you cannot do your DFAM and then at the end of the process go, oh wait, how am I going to inspect it? Is there anything that required?
Well, it's true. It's a problem, and people I know have had that situation where they have created things and find they can't inspect them, and they think, well, what do we do? Drill a little hole in it so we can kind of like poke something in and see whether it's okay inside, or it's you want to avoid that situation. I see somebody's made a comment here, asked a question. Maybe Jeff, you can help me out on this one. It's somewhere between our disciplines. What does the simulation calibration process look like? So do you have to recalibrate the model for every part? I would guess no.
Yeah, that's a simulation question. So the short answer is that if you have a good material model, like an accurate characterization of the material, and you are correctly capturing the basically the molten region, like how much metal are you melting and remelting on each pass. So how we typically recommend doing that is by creating like a wall section and then doing like a cut and etch. And typically people in this course of their process development, they'll typically have something like this already done. And you capture that, you do that cut and etch, and then you can measure for the given width and height a number of different beads. And so you can make some assessment about the volume of material that you're depositing, which is typically also associated with your feed rates of powder or wire, as well as the degree or the amount of substrate, whether that be the base plate on the first pass or subsequent layers on the subsequent passes, how much remelting you're getting. And so if you can capture that, basically the fusion zone, and like I said, you have a good material model, then that is the majority of the calibration process. The physics kind of takes care of itself from there if you have good inputs. Beyond that, when we start using some of the acceleration approaches to make the models go much, much faster, there can be some additional steps to just, kind of start with a test article like the test cone that we showed earlier. And so when you have a part that the distortion value, that you might need to perform some scaling, just because essentially when you're applying that much of the material at one time, virtually, that you can get some interesting effects. But we're trying to get away from having to do that. We're trying to generalize the approach so that becomes less of an impact. Although, this stuff, the simulation and stuff, it's still fairly new. So that we're advancing it all the time to make it better.
Jeff,
hope that answers your question.
Yeah, while we're on the topic of simulation, one of the questions was, are your simulations always layer-wise, or do you also use scan-wise simulation like a moving heat source?
So the answer is both. So we literally bring in the simulation, or we bring in the G code directly from the preprocessor. So it always starts as a full three-dimensional representation of the build, including literally all of the G code, if you want to include all of it. And then we have a knob it's literally like a knob that you twist. And if you go all the way to one end of the spectrum, it's fully transient, like it's going to match every bit of movement of that G code. And if you go all the way to the other end, it's going to apply an entire layer all at one time. And so then essentially you can tweak that knob up or down and go from, fully transient scan vector level all the way up to layer wise.
Interesting. Oh, that's super exciting. So one of the additional things that we started talking about when we were having our pre-calls were the uniqueness of the repair process versus new part manufacturing. We brought up the slide that is, Bhaskar's kind of showing that full spectrum of clad to repair to feature addition to part manufacture. We've obviously in our conversation been operating in this part manufacture side of the spectrum. But I asked Bhaskar, can you tell us a little bit about what is unique when you're using DED for repair?
Absolutely. So there's two aspects of repair. So the part here you see right in the middle here, I don't know, you guys can see my cursor, or the second from left. That's a turbine support case in Inconel 718, fairly large part, and we did repair on the seal areas inside the part. So that's a repair case from used part from the market. So the part has been out there being used in the airplanes and came out of it and worn out parts. So how do you rebuild parts that are worn out or damaged and so on? And the other aspect of the repair is repairing new parts during the manufacturing process itself. So like I was saying before, when you are printing a part that is 4,000 pounds in weight and that big and takes a long time to print, what do you do if there is a defect there? You just scrap the part. It's hundreds of thousands of dollars. So that's not an option. So it's critically important to be able to salvage that part. And for some of our other projects that we're doing is working on this kind of repairs as part of the process completion itself. So if you detect a defect, you have ability to go back and fix this. And DED is an ideal process for that. The reason being, it's unlike powder bed fusion where you need a horizontal layer powder to scan. Here, you could deposit on 3D surfaces, freestanding 3D surfaces. So let's say this nozzle, after finishing, you find a defect 2 feet below the top. You can simply go back there, grind out the defect with manual tools, and then program that in, and then go and repair that damaged area. So that's a unique aspect of DED. Now, repairing this kind of parts and repairing parts from used parts is a little bit different. Used parts are already finished condition. They have their own microstructure is already there. Parts are very tight, finished dimensions. So during repairing used parts, you got to be really, really careful about, the distortion, stresses and distortions and thermal conditions. And that's where, again, simulation may be very handy, but what's extremely important is process control, and we use our closed loop process control for that, minimizing the heat input to that area and build it back with dimensional integrity, because it's a finished part. There is no stock material anywhere, and you cannot afford to distort it anymore. So these are like two unique situations of repair, but both have its own challenges. But DED is a unique tool to do this.
If I could jump in here, Laura, I actually just had a meeting today with an aero engine OEM talking about DED for repair of components, and the dimensional control aspect is very relevant, right? So they want to be able to put in the minimal amount of heat, they have the minimal dimensional impact, but also put in the minimal amount of material. So they don't want to cut away any more material than they need to, because every time you repair a part, you need to go down to virgin material. And so if you have 20 thou to play with and you cut 20 that first time, that's the only repair you can do. Whereas if you can go 10, then you could do it twice, hypothetically, right? You can do 10 and then 10 the next time. And so being able to evaluate how you go about repairing that part virtually, and starting with a scan. So you take a geometric representation and you align that with the datum structure to be able to say, okay, where is this part now dimensionally? Like, because there's a range of dimensions, right? There's a spec. It's not just one dimension. It's a plus or minus for every data point. And then being able to evaluate how that part fits, and then say, okay, if I do this operation, if I add material right here, well, what's going to happen? Well, this part's going to start to twist and turn, and this flange is going to lift up in this direction. And how is that going to affect my overall? And the first answer would be, can I even repair it successfully? Or is it a losing proposition? At some point, you might find out that no matter what you do, you can't make it work. And at that point, it's better to just not start. And then, so there is absolutely a huge potential that I think is largely unaddressed up to this point. The tool chains that exist for not just simulation, but a broader tool chain for the digital thread workflow to enable MRO via DED and weld repair is pretty immature, but there's a lot of potential that's there. I've heard in conversations with folks about this stuff that there's some applications, some parts that have upwards of a 50% scrap rate. So out of 10 parts that come in, only 5 parts come out. That's pretty bad, right? And those are not cheap.
Mm-hmm.
Yeah, I think it's interesting how, for large type of components, weld repairs are something that has been pervasive out in industry. So absolutely. I think it's kind of cool for DED because we're able to kind of stand on a foundation of this is an extension of a welding process. So when people say, oh, you can't do that, it's like, well, you're already doing it actually.
Right. Yeah.
Yeah. So I'd like to transition to kind of get into our last topic, which is looking forward. We'll look in our crystal balls just a little bit and talk about the future of large scale AM. And I know, Bhaskar, one of the things that you were talking about, and you're already exploring this future, is that ability to do multi-material manufacturing.
Yep. Multi-material manufacturing is another, I think, is a great attribute to the AM technologies, and in particular for DED, it's a great attribute because you are pushing the powder into the melt pools. You have the ability to change the feedstock and switch from material A to material B or to material C, and apply multiple materials in the single build. What it does is a couple things. You could do part consolidation through this. So an assembly that was made with 2-3 different types of metal parts and either welded or bolted and so on. You could probably print all that together. And the biggest thing is in future, you can probably create higher performance components using this multi-material capability. In our systems, we have up to 4 materials for powder hoppers that we could add in a single build, and it all comes down to the design and so on. So here, if you see in this picture, even though it's not a correct example of multi-material, but the picture on the left shows a copper chamber cladded with Inconel on the outside, but here, the copper chamber was first built using powder bed fusion process, and then we applied Inconel on the outer surface of this and built flanges and everything there. So this is a cladding operation more than a perfect multi-material, but potentially you could print this copper and Inconel at the same time in the single build and get unique benefits out of that. But
Absolutely.
like everything else, it has got its own challenges.
Yeah.
So, Bhaskar, could you, for example, make a part out of stainless steel and then put, say, stellite bearing surfaces on it, something
Yeah,
like that?
absolutely.
So you make the bearing along with the part.
Correct. And we have, Giles, I mean, not so much for parts, but we have done a lot of multi-material tooling applications for die casting tools, as well as some injection molding tools, typically copper steel combinations. Copper extracts the heat, gets a better cycle time for the toolings, but steel gives the durability of the tool. So we have
Right.
done a lot of those. But what you just said, stellite application, we have done some of those for actually a tooling for ultrasonic AM processes. They have these toolings and those are wearing out. So we applied stellite on steel for those toolings.
Excellent. One of the things that came up during our conversation on the functionally graded materials is the simulation aspect. So Jeff, you had brought up ICME, Integrated Computational Materials Engineering, for those that aren't getting that one off the top of your head. Can you tell us just a little bit about this and where you see that kind of impacting the simulation and prediction side with specific to multi-material?
Absolutely. So the ICME topic is, I would say, probably the most complicated simulation based. It's not just simulation based, but it's the most complicated field that's coming out there right now as it relates to additive and other manufacturing. And it's a huge challenge that we're all kind of looking at and wondering how we're going to get to the future of being able to have prediction of material properties and confidence of flight worthiness, virtual certification and these sorts of things. And that's really where it's all leading towards. And when you put it in the context of multi-material or functionally graded materials, it really, and this is one of the things that DED does really well, much better, I would say, compared to powder bed fusion, because the ability to add different materials in different quantities, different alloying in different quantities in different regions is fairly unlimited, right? It's not nearly as constrained as with other technologies. But the question starts to become, going back to that question of what do I want and how do I get it? Okay, so I want it to be, more wear resistant or have a higher conductivity, or even going so far as to talk about different types of microstructure and I don't know, maybe less susceptibility to to environmentals or ablation or something like that. Well, what if I'm going to add certain types of materials, certain types of chemicals, composition and elements? Well, that doesn't necessarily get you the properties. You need to add, it's really a combination of the material, the feedstock, plus the process that results in a given property. And so the way to achieve this, really, it does require simulation. With doing it without, it's nearly impossible to do it without simulation, because you're going to need some way to define or to establish what the thermal history would be locally in that individual region. And that's going to also be dependent on what type of material you're putting down, because, copper versus steel versus aluminum or titanium, they're all going to have very different material properties. And how does it transition? Because it's also not a uniform material card, if you will, or material property. As you start to alloy it differently, that material changes from layer to layer to layer, and then you start to have it transitioning the material properties and how it impacts and affects the overall thermal and structural response. And so I would say the quick way to answer it is it's complicated. And, this is just one piece, and we're really just hitting the tip of the iceberg. We're just starting to get a handle on how to approach these problems. And it's got a long way to go.
Excellent. Yeah, I'm excited by it. And I think too, it's interesting to see as these move into supporting a more, production relevant setting, like where Bhaskar and the team are living on a day-to-day basis. And the exciting part is that I feel like it's getting there. The software is getting there. And even just seeing that in the impact on the ability to make these parts.
Absolutely. And Laura, if I just can add, we've been working, with the Hexagon team over past maybe 18 months or so, and they have done significant improvement over this short period of time in terms of computational speed and newer versions and things like that, different techniques for simulation. So it's coming along nicely.
Excellent.
Thanks,
Yeah,
Bhaskar.
it's the other thing. Yeah, it's the other thing that I always, you have to have that intersection. It requires a collaboration because each
Absolutely.
group, it doesn't know what they don't know. And so that's the other thing that I get excited about, because everyone will benefit to a certain extent from
Definitely.
collaboration and that more intimate understanding of what's going on during the deposition process. I'm looking into our Q&A a little bit. People, we've got a couple minutes, and you're welcome to put some more out there. One of the questions was on the inspection and monitoring side. It said, Giles, have you applied any inspection solution on a more online monitoring approach during deposition or between layers and beads?
Well, the answer, quick answer to that is no, I haven't. I get asked about this a lot. I have that I work with who are working on this and continue to work on it. Like, nobody's ever actually managed to solve this problem you're trying to monitor something that's a very bright light. How do you do that with an optical scanner and you can't touch it? So it's a problem. But there's another fundamental to think about here also, and that is that you would have to keep the monitoring system, the inspection system, completely separate from the machine itself. The reason for that is because if you mount the monitor on the same head, let's say, as the deposition's taking place if the say the axes of the machine are wrong, you'll be depositing wrong, but your monitor will say that it's right because it's on the same skewed axis. That's a fundamental problem that's actually prevented conventional manufacturing from achieving anything like this, and they've been trying for 300 years to solve the problem. So the answer is no, not yet.
Well, Giles, I just want to add one thing here. So you could, in a DED, you could stop the process in between and bring in the scanning instruments and measure the part intermittently.
You can.
Not every layer,
well,
but
certainly.
intermittent.
No. Well, that's absolutely true. And on large scale, you could do that at any time, couldn't you? And you could use the same technique as you use for final inspection. And if you've got something that's taking 2 weeks to run, that's probably a pretty sensible thing to do occasionally. But no, I was thinking about more like additive machines where it takes place in a box.
No,
it's a sort of start to finish process in one go.
Correct. No, I perfectly understand, but I'm just saying, because the DED is a different process, so in a big machine, it gives you the ability to bring in the measuring equipments and intermittently measure it. If you're running the part for 700-800 hours, I mean, you may want to take it
makes complete
every 40-50 hours to get at least some, idea where the part is.
I totally agree. That's quite possible with your situation.
Something I would throw in there for food for thought is, what are you going to measure against at that intermediate step? Because you're not necessarily going to want a nominal geometry at that intermediate step, because a nominal at the intermediate step would yield likely a non-nominal or out of spec result at the final inspection stage. And so
I'd have to ask a simulation guy to get an answer to that question.
Yeah, that was a bit of a leading question, right? I was teeing it up for myself.
We've established the very important and the value of the interconnected software and understanding those intermediate shapes and final shapes.
Indeed.
And with that, we do need to close our panel discussion portion. I want to thank our speakers so much. The conversation does not have to end here. We will have Bhaskar joined by Roger and Farad. and I think Rachel will also be with them. So if you're interested in basic technical engineering, all those things, visit Farad. Applications and markets, visit Roger. I will just say all things DED. Please visit Bhaskar. And then also, obviously, you'll know Jeff on the simulation side and Giles on the metrology side. Both of these groups, if for some reason you're not able to stay for networking, will be at Rapid TCT. So, oh, I missed that. Booth 1025 for DM3D and 3620. All you have to do once we spit you back out is double click on a table and you will turn on your mic and your camera and you will be part of the discussion. I will also be sitting at a table. So if you want to talk anything DED, technology development, consulting, training, happy to speak with you. So thank you for your time. And on Star Wars Day, may the 4th be with you.
Thanks, Laura.
Thank you.